Welcome back, everyone. And we're ready for the first tutorial of the series. So the presenters are going to be Swarat Chaudhuri, Yisong, Arfal Sega, and Jennifer Su. And so I will give them the floor.
All right, thank you, Armando. So first of all, we are really excited to be here, and it's wonderful to see all these faces, or all these mask faces. And because you come from a wide variety of backgrounds, we decided to start with the very basics. So here we are going to start with some discussion of just basic machine learning, and then we are going to also introduce some basic programming language concepts and formal methods concepts, and then we'll get to neurosymbolic programming. That's the plan for today.
Okay, testing. Hello. Is this on? Hello. Okay, sorry about that. Took a minute to start up. Hi, everyone. So the purpose of this tutorial, as Swarat said, is to start from the very basics. And we'll go through pretty quickly, but hopefully everyone, even if you're not from a machine learning background, can get a sense for how these methods work. And we're going to do this tutorial in 3 sessions, spanning the 3 days of this summer school at this time, 10:45 a.m. Pacific time, all 3 days. Today, we're going to go over just a basic introduction of neurosymbolic programs and neurosymbolic models. On session 2, day 2, we'll go over neurosymbolic programming algorithms, which you can think of as a form of neuroarchitecture search, if you're familiar with that from a machine learning background. And then we'll go over more advanced topics in session 3. Each session will also include a hands-on exercise, so please have your laptops ready. We'll spend about 30 minutes at the end of each session, at the second half of each session, doing a hands-on exercise. Okay, so today we're going to talk about just a basic review of machine learning, so that we're all on the same page, introduction to programming languages and program synthesis, and talk about various benefits and trade-offs in neurosymbolic models. So to start off with, just as a quick recap, most of this presentation and the presentations in the next 2 days will be based on supervised learning. And in supervised learning, the idea is to learn a function in a function class F that maps from input space X to output space Y, such that prediction error is low on a pre-collected training set. Examples include text classification, where if X is a body of text, we want to predict some property of the text. For example, is it fake news or not, yes or no? Another example is gene function prediction. If the input X is a DNA sequence, we want to predict whether or not this DNA sequence encodes a function, yes or no. We could also do real value predictions, not just discrete predictions, such as if X encodes the description of a molecule, we can predict some real value property of that molecule, such as its thermal stability. So the basic setup is you have a data set of inputs, descriptions, we call that X. We have, in this case of supervised learning, a data set of labels, we call that Y. Example here is a label, for example, ratings on Amazon, let's say. We feed those into a computer algorithm, and the goal is to come up with a function F that can approximate F of X to Y. And this function can be expressed using any machine learning model you'd like, logistic regression, neural nets, random forest, etc. So this is the basic supervised learning setup. And so once you have this set up, here are sort of the basic ingredients afterwards. So you have your training data, which I described before. From this training data, you specify what's called a loss function. What a loss function is it characterizes the mismatch between the true label and the label that your function predicts. So for example, if the true label is A and your function predicts B for this input, then this loss function characterizes the degree of mismatch. In this simple case, we're using squared loss, which is simply the squared distance of whether or not these two inputs. Afterwards, you choose a function class. Now, what is the model class that I'm going to do learning on? In this case, we're going to use linear. In this slide, of course, most of this tutorial is on neurosymbolic models. You feed both your loss function compiled over this training set and your model class into an optimization algorithm. This is the learning optimization part. And this is typically specified in this case using what's called empirical risk minimization, which basically just means that we're going to minimize the average loss over the training set of the parameters of our function class F. In this case, the parameters are W and B. And of course, since you're all interested in machine learning, you know what happens afterwards. We train a model and we profit. Now, this tutorial will focus mainly on choices of model classes, which will be neurosymbolic, and choices of learning optimization, because they need to be efficient with respect to the model class that we specify. And so when you think about what model class to specify, it's important to think about their representation power. So for example, in this example, we're using what's called a linear classifier, which basically means it learns a hyperplane or a straight line that tries to partition the input space X. In this case, the input space is two-dimensional, but in general, it's much higher dimensional, into one class versus the other class. So this is a linear classifier. You can imagine more expressive function classes that are more expressive than linear functions, such as quadratic functions that can express any quadratic parabolic curve or hyperplane. And then you could do things that, now we're going to do things that look more like deep learning, where it's sort of a conjunction of two linear models. So what you see on the right-hand side is a conjunction, yes, of two linear models. If it meets both conjunctions, then it's classified in the positive class, the purple colored class. Otherwise, it's in the negative class. And we'll sort of talk you through how to actually construct this very quickly in the next few slides. And this is sort of on the right-hand side, sort of the beginnings of deep learning. And so now we're going to talk about a deep neural network. A deep neural network first starts as its base module, what's called an artificial neuron. And so let's talk first about a single neuron. A single neuron takes its input features. These could be the original features or output features from other neurons, but right now they're just some input features. We're going to do a weighted sum. So this is actually a linear function. We're going to do a weighted sum over the input features with the weights of the parameters of this neuron. We pass this linear sum through a nonlinearity like a sigmoid or rectified linear unit, and you'll look at some of these in actually the hands-on exercise later. And this produces what's called an output feature. So this is a single neuron. This single neuron is equivalent to a linear model, such as logistic regression models. Now, a layer in a neural network is composed of a stack of these neurons. So you have this one neuron, you take another neuron, which takes as input the same inputs, but has different weights, and therefore outputs a different output feature. And this process continues until you have a layer of neurons that comprise this layer in the neural network. And the output of this layer is a vector of output features. Okay. A full deep neural network in full, and this is of course the simplest case, which is called a multi-layer perceptron, takes these layers and it just stacks them. Takes one layer, stacks it with another layer, and this process continues until you have what's called a deep neural network, multi-layer perceptron. Okay, so I'm going to go through just a little bit of linear algebra so that we understand how gradient descent works. So this is just the exact, what we see in the bottom right box is just the linear algebra formulation of a single artificial neuron. And there's nothing really that complicated going on here. I'm doing a linear inner product where W is the parameters of this neuron, and then I'm passing it through a nonlinearity sigma. And then I get this output feature H, which is the notation for a hidden layer output. If you like to think about this linear algebra, which is typically how GPUs represent this for fast acceleration, you think of it in terms of these matrices. In this case, it's just a single vector-vector product. A layer of neurons basically is just a layer of just a vector of these neurons, which you typically want to express in matrix form. So I call all the weights of all the neurons in this layer capital W. And then this outputs a vector of output features. And this can be expressed also in matrix algebra form, and so that you can get a sense of how the computation can be accelerated on a GPU. Okay, and then a full artificial network, of course, is a stack of these weights plus non-linearities. This is, in a nutshell, all that deep learning is, in a nutshell. Of course, its expressive power comes from the fact that it has many layers of these computations. And so what do these layers of computations give you that's so powerful that makes them so popular these days? Well, you can think of each layer as giving you a transformation. Each neuron is essentially a half space mapping from its input features to this output space. And the goal is to have the last layer be a separable space. So here's your first layer. Each neuron is a half space. Then you have your next layer, which whose input dimension representation is the outputs of the previous layer, and you learn another half space mapping. And after many, many iterations of this, the last layer has produced a sequence of transformations that ideally has produced a separable mapping of the data in terms of the labels. And that is why neural networks are so powerful and so popular. The reason why I walked you through the linear algebra rather quickly, but walk you through it, is for you to realize that I could train all the parameters of this deep neural network using stochastic gradient descent or differentiable optimization. And the basic idea is just to apply chain rule. Since everything that I showed you in the last few slides was just simple compositions of linear algebra and nonlinearity operations, it's all completely differentiable. You could train all the parameters of that large neural network by computing the gradient and using things like the chain rule. So basically what you learn in first year calculus, you can use to train these neural networks. And that's what makes them so powerful and so scalable. Okay, some pros and cons of the model choice. So obviously simple models are easier to learn and they have very low data requirements. Complicated models like deep neural networks are of course more data hungry and require more computation. To a large extent, that's been sort of mitigated, at least to a certain scale, by the emergence of really fast accelerators such as GPUs, which can do these really fast matrix multiplies. And that's one of the reasons why deep neural networks are more scalable than other complex model architectures, because they're readily mappable to GPU computations for fast acceleration. There are other pros and cons as well, which Swarat will talk about next, in terms of its comparison to neurosymbolic programs rather than purely neural programs, which is actually described. So just to recap, then I'll hand it off to Swarat. You have your training data. It goes to a loss function that characterizes the mismatch of your prediction and the true label in the training data. You choose your model class. Our base case is going to be deep neural networks, and then we're going to move on to neurosymbolic models. You feed that into optimization, in this case, stochastic gradient descent, and out comes a model.
Great. So so far we have seen a recap of deep learning, but now let's talk a little bit about the weaknesses, because of course, if deep learning were perfect, then we probably wouldn't be having this project on neurosymbolic programming. So what are some of the challenges over here? One challenge with deep nets is obviously their opaqueness. They're hard to trust and understand. They are really low level. And if you're deploying them in any sort of a real world safety critical application, you want to have some end-to-end safety guarantees. And that's something that's often quite challenging. There is also the matter of unreliability of training, because neural nets try to learn everything about the world from data. As a result, learning is often unreliable and depend on low-level facets of the training environment. And in order to fix these issues, you often need just a tremendous amount of data. And then finally, there's the issue of the inductive bias that the model uses to generalize, that being opaque to humans. So there is this possibility then that the neural net may learn some patterns from data, but this may completely contradict all the common sense knowledge we have about the world. And so as a way around all of these issues, really, we in this project are thinking about using symbolic knowledge, or in other words, code or programs. And so let's just understand this concretely, what we mean by this. Suppose you're trying to drive a car, right? So you have a self-driving car and it's interacting with the environment, and at each point it's taking an action, and then the state of the world is changing as a result, and the state of the car, and then based on the quality of the action at the current state, you're getting, let's say, a reward. So how would you solve this problem? Well, human control engineers have been solving this kind of problem for a very long time. And there are all these controllers in control theory that are very well established. One thing you could do, for instance, is that you could write a PID controller. And here what you do is that you have let's say, a target velocity, and you have a current velocity. And so what you do is that you look at the delta between what you're trying to achieve and what you currently have, and then come up with a linear expression that is going to adjust the value of your acceleration, for example, and that's going to change the velocity. So you can do this even more in a more complex way. So for example, if you find that, maybe there are two modes in which you could drive. Sometimes you drive fast and sometimes you drive slow. And for instance, you could decide that if the car is aligned with the axis of the track, then you drive faster. And otherwise, maybe you are a little bit misaligned, you need to turn, and as a result, you need to slow down. So you could write things like this as a human engineer. So contrast this with the other paradigm, which is more recent, which is that you learn this kind of a controller entirely from data. So here, what you'd be doing is that you'd be taking various kinds of actions at various kinds of states, and you're going to be seeing the result that comes out of taking those actions. And then you're going to learn a controller that's going to give you profit, right? And now what's a representation for this kind of controller? Well, you could imagine using a neural network because of their advantages regarding training. So, so that's what you do. But then, of course, this comes with many of the challenges that we have already mentioned. And so what we are imagining over here is a mix of the two. So we are imagining a situation where you are not using either the purely neural controller or the purely programmatic controller, but a combination of the two things. And one way in which you can achieve such a combination is what you see on the right over there. So it's a basic linear composition of the two kinds of controllers. And one way to think about it is that you are doing most of the work with this manually written PID controller, but you are allowing the controller some bit of extra flexibility that is learned from data. Another way in which you can think about it is that you are doing learning, right? But you are adding the symbolic controller as a regularization term in order to bring some discipline into the learning process. And this is, of course, just one example of ways in which you could compose the symbolic and the neural pieces. There are many, many other ways in which you can do this. And we are going to see actually examples of that in the next couple of sessions of this tutorial. So what do you get out of this? And so here's a video of a car that is being driven by a neural network purely versus a neurosymbolic model. So on the left, you have the regularized neurosymbolic model. And so what we see is that early on in the training process, the purely neural car is just all over the place, whereas the neurosymbolic car is behaving a lot more reliably. And in the real world, this is often going to be the situation. There is often not going to be, a tremendous amount of data available from, realistic simulators. So this sort of an idea might make sense from that point of view. And this idea, by the way, you can apply to other settings as well. For example, Yisong and his collaborators have applied these sorts of ideas in the setting of continuous time control. And so here, the symbolic part of the model is a collection of differential equations. And you can use this sort of a neurosymbolic model to capture the dynamics of the environment as well as the controller. But here, it's capturing the dynamics. And so what this is doing is that imagine that you have some equations of the world, but they're not absolutely perfect, right? So there are some boundary conditions and edge cases where things just aren't captured perfectly. And that's the part that you capture using your neural network that is learned entirely from data. At the same time, you're not just completely throwing away all of this knowledge that physicists have collected over centuries, right? This has been applied to a wide range of settings. For example, here's an example of a drone that is maneuvering using this kind of a neurosymbolic dynamical model. And it turns out a lot better at navigating boundary conditions when you're really close to the ground. At that time, you are not following the equations of physics, the standard equations perfectly, but that's captured from data. Other examples, environments that are highly dynamic, multi-agent interaction. So there's a whole lot of work that's going on in using these kinds of models. And by the way, since the one big theme in this project is scientific applications, I'll also add that scientific knowledge you can think of as code as well. Go back to equations like E equals mc squared or Newton's laws. These are all ultimately code, human written code. And one could imagine perhaps combinations of these sorts of codes with learn knowledge in the form of neural networks. And so here are two concrete examples of this idea. So this is from linguistics. So we have a lot of linguistic knowledge about how various sorts of tenses are constructed. And again, the idea is to use this sort of symbolic knowledge, in the biological setting, which is one of our big applications in this project. We have also a lot of biological information, and that's also something that you can combine with learned knowledge. So there is a very rich space over here, right? So symbolic programs, on the one hand, they have the advantages of being interpretable, verifiable, making use of structured domain knowledge that human minds have constructed over a very long period of time. And as a result of using this domain knowledge being more data efficient, on the other hand, you have neural networks, and they're scalable, they're flexible, they can handle messy data, and it's really easy to go and code up a neural network, as you will find out very soon. Many of you are already experts at machine learning, but even those of you who are not, you're going to actually play with some neural nets in the hands-on part of this tutorial. So that's the model side. And then on the side of algorithms, you have program synthesis on the one end and machine learning on the other end. Program synthesis algorithms are building on a lot of work in formal methods, programming languages, and also classical AI. So ideas such as heuristic search, solver-based search, use of automated deduction to do pruning, version spaces. On the other end, you have machine learning, contemporary machine learning. You're going to be using scalable stochastic gradient descent methods, sampling-based optimization, approximations such as variational approximations, all sorts of ideas like this. And they'll all come together in the sort of learning algorithms that we are going to talk about. And so neurosymbolic programming is the name that we have collectively given to this, this space where you have on the one end neurosymbolic models, and also you have neurosymbolic learning algorithms where you're bringing together ideas from symbolic AI, formal methods, and deep learning. By the way, just a shameless plug. So here's a survey that some of us recently wrote up over here on neurosymbolic programming. And if you're interested in this tutorial, you could go and look at that survey. There's a lot more information there. Okay, so then just to give you the overall picture over here. The basic problem setup in neurosymbolic programming is that it's the same as what you have in machine learning. You have data, and you're trying to learn a model out of that. But then there is an additional piece over here, which is that you have a definition of a programming language, a domain-specific language that is going to describe the space of models, right? So you have a lot more flexibility here. It's not just that you have neural nets of depth 3, you have a rich DSL in which you can describe these models. And then we are also going to look at a version of this where you have additional constraints on top of this. And these constraints could be, for example, safety properties and reachability properties and so on. But in the first couple of lectures, we are not going to consider that part. So just to give you a very high-level overview of what a DSL looks like. So if you open a Pale textbook and you look at, how do people introduce programming languages? So there are these two pieces, one part being syntax, the other part being semantics. Syntax is what do programs look like? And that is typically given as a grammar. And so here we have one such grammar for the kind of controller that we saw earlier. So here alpha represents program structures, right? And so what it's saying is that, so this program takes in a state as an input, and then just a basic action could be a program in itself. Algebraic operations applied to a bunch of these program structures and also the current state that could lead to a program too. You could even have predefined parameterized functions. So you could imagine this being neural networks, right? This plus thing at the bottom. And these capture, possibly prior knowledge, but they could also be, new learnable modules. And that could be a program as well. And you could have, if then else's, and you could, go crazy. You could add, recursion and loops and anything you really want. And then this is what programs look like. And the program semantics is implemented using an interpreter. And we are not going to go into the details of that, but think of it as, you probably have built up expression evaluators in some programming classes. So here it's just a fancier version of this, right? You are telling us what the program does on a given input state. And so that involves, writing up an expression evaluator essentially. And I mentioned, by the way, earlier additional constraints. And so there are all sorts of things you could write over here, starting with basic safety invariants, all the way to temporal logic properties. And we are going to talk about this sort of thing in the very last part of this tutorial on day 3. So then coming back to the definition of neurosymbolic programming, you have a DSL that is given to you in the form of a grammar, and there is also an interpreter, right? And this is something that's coming in as input to the learning algorithm. And the learning algorithm also has a loss function, a learning objective. And then the cranks are turned, and then out comes a neurosymbolic program. And then this is something that you can use potentially in downstream analysis. And once you do that analysis, you may decide, for example, to change the learning objective, that is update the loss function, or in some cases, you might even want to update the DSL. For example, you may have learned new modules out of this downstream analysis, and you may augment the DSL with these extra modules. And so there's a very rich space over here. It's not a new idea, the idea of neurosymbolic learning. It in fact goes back to the late 80s. But just as deep learning wasn't new either in the 2000s, the ideas had been around. It's the same way here. There have been lots of advances in formal methods and deep learning over the last decade. And now is the time to bring these ideas together and push for something that's bigger than the sum of the parts. Now we are going to, there is an opportunity for amazing algorithms here, and there's a lot of applications in the sciences and autonomy and other settings. So we are really, really excited, and we hope you are too. And now we are going to move on to the hands-on part of this tutorial. But before we do that, very, very quickly, just a few observations. So note that if you take that problem statement and if you fixed a program structure, right, then basically you have deep learning. You can then you then have a problem of doing parameter learning using gradient descent, and in particular, if you set the program structure as a neural network, then you just have deep learning. And then the problem of finding alpha, the program structure, that's analogous to neural architecture search. But here, of course, it's a space of architectures that's defined by a DSL and has some symbolic semantics. So there is it's potentially a lot richer than just classical neural architecture search. Here we are going to build on a lot of prior knowledge from classical program synthesis, but there the focus is primarily on alpha, the theta, the parameters being very simple. So here really we are going to bring together ideas from these two spaces. Okay, and with that, we are going to move on to the hands-on activity. So Jennifer, would you like to take over?
Yeah. Oh, thanks, Swarat. Yeah, so hi, I'm Jennifer. I'm here to introduce the hands-on activity, which is based on one of the areas we're really interested in, which is applying neurosymbolic programming to help scientists do data analysis, discovery, as well as interpretation. And so to be more concrete, the area that you'll be walking through in your notebook is going to be focused on behavior analysis in science, which is focusing on the question of how we can go from these videos of observed behavior to frame-by-frame annotations or labels of the animal's behavior. And this question is important to a wide variety of scientific fields. For example, in behavioral neuroscience, we want to study the relationship between this observed behavior and neuroactivity in order to understand the relationship between brain and behavior to help us better diagnose and treat neurological diseases. This also comes out in fields like drug discovery, where we want to understand how the effect of different drugs have on these model organisms, such as mice or other organisms, and do pharmacological evaluations. Again, behavior comes up in many different fields. They're also useful for studying strain variations, in how changes in the genotype of the animal might affect their social or individual behavior. And so your hands-on activity today is focused on this question of how we can categorize behavior at each frame. And traditionally, how this was done was with manual frame-by-frame annotation of the animal's behavior, which you can imagine is very, very time-consuming. It actually takes over 100 annotation hours to annotate each day of recording. And this is not scalable as we ramp up the amount of data we're collecting in these scientific experiments. If we want to study more organisms or more behaviors, we then have to go back and manually annotate our videos again. So automatic behavior quantification is key to moving this large-scale data collection forward for behavior analysis. And of course, people have worked on this for a while. So one way of automatically quantifying behavior is to start from these videos, like you saw earlier with interacting animals, such as mice. Do key point estimation at each frame, where the key points correspond to the body parts of the agents as they're interacting. So here, these key points correspond to XY positions of different body parts, like the nose, ears, hip, neck, and tail of the animal. And finally, going from key points, we can then train behavior models to classify behaviors at each frame. And of course, doing this whole pipeline would take way longer than a 30-minute tutorial. So we have already put together a data set for you to use, consisting of millions of frames of trajectory data, so we've already done the post-estimation step. And we have already gotten also millions of frames of behavior labels from domain experts. So the data set processing step is all handled for you guys. And we give you a subset of this data set for the tutorial, where the goal for you now is to take this data set and use neurosymbolic programming to learn the relationship between pose and behavior. In addition to the trajectory and behavior labels I've mentioned, behavioral neuroscientists have already worked on this for a while, so they already have existing domain knowledge in the field. So we provide raw trajectory, behavior labels, as well as the behavior attributes, which captures the domain knowledge that these experts use for behavior analysis. And you can see some examples of the features we provide. There are features that you can compute on top of key points. For example, facing angle between the animals, distance between animals, head-body angle, speed, acceleration, which you'll have access to in your notebooks. So I'll briefly go through the code structure before giving you guys a link and letting you jump in. So the first part of the code, we'll have some code for you for visualizing the data. So the trajectory data of the animals, as well as the behavior labels at each frame. We also provide code to train a neural network in the form of a 1D convolutional network to capture the temporal structure of these behaviors. The next part, we have given you a program architecture, but you also have the space to modify this structure to see if you can learn a better program. We also have code for visualizing model weights. And finally, we end with an open-ended exploration. So just jumping in so that you guys can get started. To access the code and the instructions, you can use this bit.ly link. So the link is bit.ly/neurosym. There's also a QR code that's literally the same link. And you'll have 30 minutes to walk through this notebook. Please raise your hand if you have questions, since we'll be walking around the room. And we really encourage you to work in groups to meet some neighbors, in groups of 2 or 3. But of course, the notebooks can be completed by yourself. I just include the Wi-Fi information here in case you need it. And I'm gonna let you guys jump in.
Thank you.